chapter 12. And last time we talked about a couple of things, kind of important main things there. We talked about Q, which is the reaction quotient. And Q is calculated the same as K. So if you want to calculate Q, that is your basically products over your reactants. Just like you do again with K, you do have to take the coefficients into account and use them as your exponents. We can use Q if we know Q and K to determine a couple of things. And if Q is greater than K, it first means that you are not at equilibrium. And in order to reach equilibrium, you will need to make more reactants, basically. It needs to head in that direction. If you do calculate Q and it does equal K, then you are actually at equilibrium at that point. If you calculate Q and it's less than K, you again are not at equilibrium, and you need to kind of head towards the product side to reach equilibrium. So we talked about and sort of did a problem as well, sort of a straight up sort of Q type problem. And that's usually the question you're asked is, is this system at equilibrium? And if not, which way it needs to go to reach equilibrium? There's another instance where you'll use Q or can use Q. Remember, to do Q or to calculate Q, you really do have to be given sort of the initial amounts of everybody. So if you're not given the initial amounts of everybody in the reaction, there's no way for you to possibly calculate Q. But if you are, you in a lot of cases should calculate Q. We then talked about really the main sort of calculation here of the class, which is ice tables. Something like that. And when we solve equilibrium problems, when we're just given initial concentrations, we do an ice table. And we take our initial, for example, of A and our initial of B. And if there is nothing mentioned to you about the product, it is safe to assume that it is 0 to start with. That also helps you for the change part as well, since you really have no products there to begin with in this situation. We could probably safely assume that the forward direction of this reaction is going to be taking place. The result of that is our reactants should start to decrease with time as we need to make products, and our products should start to increase with time. So remember, the change part is really the most important thing, really almost in the ice table. And we use that as minuses or pluses. We go minus x in this case. We do take the coefficient into account. So in this case, since the coefficient is 1, it would be minus 1x. If the coefficient was 2, it would be minus 2x and so forth. Here, this would also be minus x. The coefficient here is 1. When we come to our product side, this would be plus 2x, again, for the coefficient. The coefficient is really important because it does take into account basically all the stoichiometry, the mole-to-mole relationship. So if you do not use, obviously, the coefficients, your calculation is definitely going to be wrong because you won't have really the right mole-to-mole relationship. When we're all done here, we're basically going to just drop these guys down. At this point, as we talked about last time, we could actually use our equilibrium expression here. And maybe we knew what it was, say it's 40. We could then take our equilibrium line and basically put it into here and solve for x. Now, one of the ways that we could solve for x is to use the quadratic like we talked about last time. And in the quadratic there, you end up with an equation that looks something like this. Ax squared plus bx plus c. Again, that gives you a, b, and c. That goes into our quadratic formula of x is equal to minus b plus or minus the square root of b squared, thank you, 4ac divided by 2a. As we talked about last time as well, again, this is going to get you 2 answers, obviously, when you do it. And there really is all the combinations that you possibly could get. Again, you could get positive, negative numbers. You could get 2 positive numbers, and you could also get 2 negative numbers, believe it or not. And what determines which x value you should use is because those x values that you solve for are essentially all the x values here in our table. Obviously, when you go and put one of those values back into any of those uh, equilibrium line, it will yield you a negative concentration or negative pressure. You cannot have anything that's negative, so that is usually, how you can eliminate it. So a lot of times it is the negative number that you kind of can eliminate. But I will tell you, there's some occasions like you could get two negative numbers and only one of them will actually give you a negative number when you put it back in. So just keep that in mind. Once you do that, you can put it back in here like we talked about. And we did in that little example when we finished up on last time. And that will give you the equilibrium concentrations of everybody. And since it is, like we talked about at the end there, math, you should at that point be able to, if you want to kind of check yourself, make sure maybe you didn't make any type of mistake, you could put that back into the equilibrium expression and it should basically hit the equilibrium constant value. It should be fairly close. Again, it may not be exact with rounding and stuff like that, but it definitely should be in the same ballpark. Now, you could do these ice tables in molarity. You could also do this type of ice table with pressures as well and use like a Kp value like we saw earlier on in this chapter. If you are going to, as we were talking about earlier, do an ice table, atmospheres, once again, is the unit that you need. Even if, like I mentioned earlier, they give it to you in some other unit like torr or something like that, and they want the answer in torr, you do need to slap it into atmospheres before it goes into the table. And afterwards, after the table, you can then convert it back to whatever unit you want. But it does need to be atmospheres as you go into the table. Now, speaking of this, we talked about Q a second ago and last time. And again, there typically is a Q-type problem. The second place where you could potentially and should potentially calculate Q is in a calculation like this. So if you come across a calculation like this and it disappears but comes back, and you have all of the, so no zero here, but you have all of the starting information there for your table, you should calculate Q. And the reason you would want to calculate Q in this case is it is probably not at equilibrium because frankly, it wouldn't be much of a question at that point if it was. But more importantly, it's going to tell you which direction this reaction has to go to reach equilibrium. So for example, let's just say that we did this and we calculated Q and it was greater than K. That tells us, obviously, as we just talked about, that is not at equilibrium. But in order to reach equilibrium, this reaction actually has to head in the reverse direction, right? And that would affect your ice table calculation. How? What would change? Yeah, so what would happen in this case is this guy over here would then be decreasing with time. So instead of pluses, it should be minuses. And these guys would be increasing with time, which means these guys should be pluses. So if you do have that situation where you do have enough information and everybody sort of information at the beginning, you really should calculate Q. Again, in that situation, like I said, it probably will not be at equilibrium, but it will reassure you, for example, in terms of your calculation, which way that sort of change needs to occur. And you actually could calculate it, for example, if we had this situation, you could calculate it in one of two ways. You can change the pluses and minuses to the correct sides. And if you did that, you would still use the same K value that was given to you in the problem. If you decided to reverse the reaction, what would you have to do to the K value? You'd have to take one over the K value, and then you could do your normal minuses on the left and pluses on the right if you reversed it. So you actually could work it both ways. It's whatever you kind of prefer to do. But if you do reverse the reaction, sometimes people do that, they reverse the reaction, but still use the same K. Remember, you would have to adjust the K value. So if you don't have to worry about kind of adjusting the K value, in addition to that, in this situation, you could actually just leave it the way it is and just change the pluses and minuses, obviously, to the other sides and stuff like that. Any questions on that there? All right. So we did one, so seems like it's your turn. There you go. So why don't you give it a go here? We have this reaction here, a mixture of 0.5 moles of H2 and 0.5 moles of I2 are placed in a 1 liter flask. What are the equilibrium concentrations to everybody if the equilibrium constant value is 54.3? So take a few moments there, work it out, see what you come up with. I would probably do an ice table, I imagine. Usually a safe bet. Okay, so let's take a look, see how you're doing. So clearly, like I said before, probably usually a good choice, an ice table in this class. So um, we have moles and we have liters, so we do want some concentrations. So we'll start there. So our concentration of H2 is going to equal 0.5 moles divided by 1 liter, so that's not too bad. 0.5 molar. We'll get the same concentration there. Looks like for I2, 0.5 moles divided by 1 liter, 0.5 molar. We also could write our equilibrium expression for this. So it's going to be our products, which is HI. We do need to square it once again because of the coefficient that is there, divided by the concentration of H2 and the concentration of I2. And that is going to equal 54.3. Questions so far here. All right, so we'll do our ice table here. Borrow that there, I think. So initially here, we had 0.5 molar, 0.5 molar, and there was no mention of anything about the product. So once again, it is pretty safe in that situation. And I'd almost say like 98, 99% of the time to assume that perhaps you got zero going on there. And we have our expression. I'll just rewrite it over here one more time. It would actually tell you in the problem. Yeah. So again, there was no mention of anything about the product concentrations or anything like that. So if they don't mention it, it is safe to assume that it's zero. Clearly, if they said something like, "Hey, it's this concentration," then obviously you would have an initial. So that's what you would want to look for. And it does happen. There definitely be situations where you will have some stuff on the product side as well. And sometimes people kind of after a while gloss over and always kind of automatically put zero over there on the product side. So just try not to get into that habit and just make sure you don't miss it. Here we're going to do our change, and because we really had no products, we again could assume that what's going to happen here at the beginning is the forward direction of this. So this is going to put like our minuses and pluses on the side we're kind of used to it at. This is going to be minus x, and plus x. This then will get us to equilibrium, 0.5 minus x, 0.5 minus x, and this is x. Any question on the table here? All right, so in this case, we do want to solve for x. So we're going to take everything that's at the equilibrium line there, and we're going to put it into our table, our expression. That will get us here x squared basically up on top, divided by 0.5 minus x times 0.5 minus x, and that's going to equal 54.3 at this point. Now, hopefully you looked at that and decided that looks like a perfect square on both sides. Yes. It should. Thank you very much, actually. Thank you. I did miss that too right there. Thank you. Yeah, so obviously should have a 2 there, and that would get us basically 2x. I'll put my parentheses there, square. Thank you very much. Yeah, so definitely don't forget the coefficients like I did there. Bring my 2x down there. Now we're in business. All right, so we do want to solve this, and here hopefully you can see it is actually a perfect square on both sides. So you can square root both of them. You could also quadratic it if you had the time, I suppose. They should come out the same, by the way. So if I take the square root of both sides, again with my correct value there, That's going to give me 2x up on top. That'll give me just one of these guys here on the bottom. And the thing I sometimes myself forget to do, actually, you want to take the square root of 54.3, which will give me 7.36885. That looks a lot easier maybe to solve. So we're going to multiply what's on the bottom to the other side. And that will get us 2x is equal to 0.5 there. 3.6844. Take it to a few digits. Minus 7.36885x. I'm going to combine my x's in this case. So I'm going to take this guy, which is subtracting, going to add it to both sides. And that's going to give me 9.36885x equals 3.68442. Lastly, here we're going to divide to the other side. And that's going to get us here. Yes. Okay. We'll get an x is equal to 0.393 in this case. Yeah. Any questions on that? Yeah. Richard? Right now?
Yeah. So the question is so we don't need to find it for this one?
Yeah, so that's a good question. Is there a way I could actually calculate Q in this case? The answer is you really can't because you don't have that product concentration, right? So the only way you can calculate Q is if you're given the concentrations of everybody. So in this case, we were not, so you don't have to worry about Q. It's only really a situation when you're doing these type of calculations if you're given everybody's concentration to begin with. And the reason for that is pretty simple. If you're given everybody's concentration at the beginning, clearly the reaction is happening, so you don't know if you're at equilibrium or not. You're probably not if it's this type of question, but also it helps you understand which way it needs to go to get to equilibrium. In this situation, because we were not given any products, there is only one way this reaction can actually proceed to begin with, and it has to go to the product side because there is no products to start with. Other questions? All right, now that we have our x, we could actually get our values here. We'll go H2 is 0.5 minus x. That's going to give us 0.5 minus 0.393. And we will end up with a 0.107. We do need some units there since it is a concentration. Our I2 will come out the same. 0.5 minus 0.393, 0.107 molar. And lastly here, just over here, I think, concentration of HI at equilibrium is equal to 2 times X. So 2 times 0.393, gonna get us there, 3 or 0.786 molar in this case. Once again, you can check to make sure you didn't mess anything up by putting that back into the equilibrium expression there. And again, you should get basically the same value as our K. If you squared it and then divided by 0.107 twice. And if you do, you get about 53.96 or 54, which obviously is pretty close to where we were in terms of our equilibrium constant. Again, like I said, if you did not see the perfect square here, but did take the quadratic path, it really should give you the same answer at the end. So you could always just roll with the quadratic if you want, and it should really get you the same answer, obviously, as you did some other way. But here, if you could recognize it as a perfect square, it can save you some time, obviously, than having to kind of go through the quadratic and all that. Any questions on that one there? All right, let's try another one here. We're going to do basically the same equation, but we have 0.00623 molar H2, 0.00414 molar I2, and we're starting with 0.0224 molar HI. Same equilibrium constant there, 54.3. And again, we're looking for every base concentration. So give it a go, see what you come up with. Let's see how we're doing. So we're doing the same reaction here. The difference though here, we are given the concentrations of everybody here. So as we've been talking about previous to this problem, this would be a situation where you would want to calculate Q because you do have the ability to do so. Again, probably in the case of this problem and most of these problems you would be doing like this, the answer is going to be Q is probably not at equilibrium. But again, it will reinforce sort of which way the reaction is traveling there to get to equilibrium. So the first thing we'll do is we'll calculate Q. Q again calculated the exact same way as we do our K. So we'll square our products there and our reactants happening there. Here we're just going to put in our really initial concentrations to again answer the question, are we at equilibrium? And again, which way we need to go to get there. So 0.0224 squared divided by our H2, which was 0.00623 and our 0.00414 for our I2. And if we do that there, 0.0224 squared divided by 0.00623 and divided by 0.00414, it's going to get us about a 19.5 as our Q. And in this case, Q is less than the K value of 54.3. So this tells us, like we would assume, like I said, it wouldn't be much of a problem if it was at equilibrium. It's definitely not at equilibrium, but the more important thing here is because Q is less than K, we do know it needs to proceed towards the product side here to reach equilibrium. So now we know, like kind of normal here in this particular case, our minuses are going to be on the left and our pluses are going to be on the right. So again, if you skipped over Q in this case, you got lucky in a sense, and you might be okay in a lot of cases because it is going in that direction. But again, this would be really the second place where you would want to sort of calculate Q if you came across this situation. Any questions on that there? Now that we kind of know it is going to head like we think, we could actually get to the calculation part here. We are going to do an ice table here. There it is. So we got H2 plus I2, and that goes to 2HI. Going to give us our same equilibrium expression of HI squared divided by H2 and I2. Going to equal our 54.3 that we saw there. So initially here for H2, we got 0.00623. For I2, we got 0.00414. And again, in this case, this is not going to be zero as we were given an initial concentration, right, of our products. So we do need to put that into our initial line here. And again, really the purpose as to why we calculated Q there, right, to verify which way it's going. Our change, because we know it is going to go to the product side, this is going to be minus X. I'll try not to mess this one up, plus 2X here on our product side. That means at equilibrium here, 0.00623 minus X, 0.00414 minus X, and 0.0224 plus a 2X in this particular case. Any questions on the table? Remember, also a common mistake that sometimes people make is they're so used to doing minuses of X's, they kind of do minus on this side as well. So again, it is plus on that side. That's going to go into our expression, which will give us basically 0.22. I missed a zero there. There we go. 0.0224 plus 2X squared and divided by 0.00623 minus X and 0.00414 minus X as well, going to equal 54.3. Unfortunately, this is not a perfect square situation, so we do need to do some factoring out type of deal. So I'm just going to kind of do it in pieces maybe, and we'll kind of put it back together here in just a sec. So if we do our top part first, which is up here, that basically is 0.0224 plus 2x times 0.0224 plus 2x. Again, we're going to kind of multiply in and multiply out to do that. 0.0224 times 0.0224 gonna get us go up here 5.018 times 10. I'm just gonna do a little scientific notation here. 1, 2, 3 minus 4 looks like, I think, if I'm not mistaken. We will then have basically, so we're gonna go here and then go there, right? So plus 2 times 0.0224. 0.0448. They clearly saw the problem out there. And we're gonna do the same thing on this side. That's gonna get us, that was kind of what I was saying in my head right there, 0.00448x. And I'll kind of go underneath there, and 2x and 2x is going to give us 4x squared. Kind of cleaning it up here, that's going to get us 4x squared plus we got basically 0.0448 plus 0.00448, gonna get us a 0.0896, I believe, x, and 5.018 times 10 to the minus 4 in that case there. Any questions so far? So that should be what really goes up there on top. Now we're going to do basically the same thing for the bottom. So maybe I'll do, yeah. Yeah. You don't have to. You could write it with the zeros, just don't lose a zero along the way. You know, obviously some of them may have a lot of zeros, so it's okay. It may be better to on ones where you see there's a lot of zeros, especially if you're doing something like this where there's a lot of numbers you got to kind of move around. Then maybe put it in there, but you don't have to. Just you gotta be careful. Yeah. We'll go bottom here. We'll do it in blue. Just gonna go that way. All right, so same deal here. We're gonna go 0.00623 minus x, 0.00414 minus x. Once again, we're gonna go in and out, which sounds really good right about now. We'll do that as well. So we're gonna go 0.00623 times 0.00414. That is going to get me, again, I can go scientific notation on this one, 2.58 times 10. We got 1, 2, 3, 4, 5, I believe, minus 5. 1, 2, 3, 4. Well, yep. All right. Then we got minus basically 0.00623x minus 0.00414x, and I'll go underneath as well, plus x squared. Again, kind of combining our middle terms there, going to give us x squared. We got 0.00623 plus 0.00414. So that's going to give us a minus 0.01037x, and we then should have a plus 2.58 times 10 to the minus 5. And again, that is what technically should go on the bottom there. Just going to borrow that there here. And up on top, we had 4x squared plus 0.0896x plus 5.018 times 10 minus 4. All right. So I'm just going to flop a page here and put everything back together in the right spot there. So if I copy it down right there, 4x squared plus 0.0896x. And that's going to be plus back here since I scribbled badly. 5.018 to minus 4. So that's what we got for the top after we kind of factored it out. And on the bottom there, x squared minus 0.0103, 0.0103. 37x plus 2.58 times 10 to the minus 5. That's going to equal our 54.3. At this point, we need to take whatever's on the bottom and multiply it right to the other side. So we're just going to take everything there and move it. Up on top doesn't change, so I'll just recopy what's on top there. 4x squared plus 0.0896x plus 5.018 times 10 to the minus 4 equals, that's going to get us 54.3x squared minus 0.01037 times 54.3, 0.563, I'll call it 1x, and 2.58 to the minus 5 times 54.3, 0.001401, we'll call it. We now need to combine everybody to one side. So again, it really doesn't matter which way you go, but I'm going to bring everybody from this side over to that side. Yeah. So that means I'm going to take basically 54.3 and minus 4. And that'll give us obviously 50.3x squared. This second guy here needs to be subtracted to the other side. So we're essentially adding those two numbers, 0.5631 plus 0.0896. And that's going to be a minus 0.6527x, I believe in this case. And lastly here, we got this guy. And we're going to subtract that to the other side. So 0.001401 I did, I think. And we're going to subtract 5.018 to the minus 4. And that's going to get us a plus 0.00089992 equals 0 in this case. Again, give or take, should hopefully be close on the numbers, with rounding maybe a little different depending if you round it slightly different. This should be A, B, and C, I hope, in this case. Let's see here. So we're going to go into, obviously, our quadratic in this case here. All right, let's see. So we'll go x is equal to minus b, which would be 0.6527, plus or minus the square root of b squared, 0.6527. All right, so we got there. Just come here. 0.6527 squared minus 4 times a, which is 50.3, times c, which is 0.0008992. That gets us inside the square root 0.245098. If we take the square root of that there, gonna get us 0.495, I'll call it 1. That's all gonna be divided by 2 times our 50.3, which is 2 times a, 100.6, I hope, yeah. That's gonna give us 2 x values, and we're gonna hope for the best here. Let's see here. There was a lot of screaming in the middle of the problem there from outside. So it gives us an x of 0.01141. And if we do the subtraction here, gives us an x of 0.00157 in this case. Now we can obviously eliminate the top guy, because if we go back to our equilibrium line there for H2, it is 0.00623 minus x. Our I2 was 0.00414 minus x. And our HI was 0.0224 plus 2x. So obviously the first one that I eliminated is bigger than these two numbers, so that would get you a negative number if you put it in there. So let's put the other one in and see what we got. So That means at equilibrium for H2, 0.00623 minus 0.00157, 0.00466 molar for H2. For I2, 0.00414 minus 0.00157. So I2 would be 0.00257 molar. And lastly, 0.0224 plus 2 times 0.00157 gonna get us for our HI 0.0255 molar, I believe, in this case. And if we didn't screw up anything, we hopefully have the right number there. That would be good, I hope. There we go. And if you put these guys back in, again, you should get about 54 and some change, which I hope you do, because I don't want us to go back and change it again. Yeah. Any questions on that one there? So this one, a little bit more math. Yeah, so we've all done this one. Any questions along the way? So obviously you do want to be careful if you kind of move things around like I did, kind of did them separately. Just make sure you don't lose a zero along the way. I'll be honest with you, I lost a zero along the way when I did it the first time. So, you know, it happens. So just got to be careful as you go through it. Any questions on that one there? All right. I think we do get 54. I guess I should throw it back in just to make sure. 0.00255 squared divided by 0.00466 divided by 0.00257, 54.3. Not bad. Pretty good. Any questions on that there? All right, let's try one more now that our math is warmed up. Hopefully it won't cause screaming outside again. All right, if the Kp is equal to 4.31 times 10 to the minus 4, in this case, we're actually looking for the pressures at equilibrium. If we started with 0.862 atmospheres of N2 and 0.373 atmospheres of H2. So again, as we talked about previously, even though it's all about pressures here, you can do it the exact same way as concentrations. Yeah, so you go into your ice table and solve it the same way. Okay, so let's take a look at this one here. So as I mentioned earlier, absolutely no problem here because it's in pressures. It's not a big deal. Again, the only thing you do have to worry about, as we talked about earlier, is if it's not in atmospheres, it does definitely need to be in atmospheres before it goes into the ice table calculation. We could proceed like normal. In this case, we are given the pressures here of N2 and H2. So just like we saw with concentration, we are actually not given everybody's pressure, so we don't have to worry about Q or anything like that in this situation as well. But we could just roll through our ice table here like normal. So I'll borrow that. We could also write our Kp expression, and that would be the partial pressure here of NH3. We do need to square it because of coefficient. That's going to be divided by the partial pressure of N2 and the partial pressure of H2, which also needs to be cubed because of coefficient. That's going to equal there, looks like 4.31 times 10 to the minus 4. So doing our ice table here, initially for the N2, we have 0.862 atmospheres. For the H2, 0.373. Once again, you're not told really anything about NH3, so it is again acceptable and safe to assume 0 as your starting pressure in this case. That also then tells us, like we did previously, that we should expect that this reaction should be heading in this direction towards the product side. And that would be our minuses on the left and our pluses on the right. So we'll put those in. It's going to be minus x minus, once again, 3x because of our coefficient. And this will be plus 2x again because of the coefficient here. That means when we do get to equilibrium here, 0.862 minus x, 0.373 minus 3x, and 2x. Any questions on the table there? So again, pretty much identical how you do it with molarity and so forth. Just like everything else, we're going to go into here and solve for x. So putting that in there is going to give us 2x is going to be squared divided by 0.862 minus x. 0.373 minus 3x, and that does need to be cubed, and that is going to equal 4.31 times 10 to the minus 4. Here we do need to solve for x, so clearly at this point we should just go to the next problem because this does not look like fun, right? Nobody wants to do that. So clearly nobody wants to do the math part of that. So in this case, we want to think about a way that maybe we can get around it. And one thing that we can actually do in this situation is when I look at the K value here, the K value in this particular case, is that considered a large or a small K value? That is considered a small K value. And because I have a small K value, what that means is when I reach equilibrium, should I mainly have reactants or products? Small K value means you should have reactants, right? Products over reactants. So we should end up with a lot of reactants here at equilibrium. And because we're going to end up with a lot of reactants at equilibrium, that means that when we think about the change part that's occurring in this reaction, it's going to be relatively small, right? Because it's not going to really head to the right. It's going to kind of hang out over there on the left-hand side. So because the change is going to be relatively small, and we definitely don't want to do that math, we can assume in this case that x is equal to 0. And we can make this assumption that x is equal to 0 because we have a small k value. So when you have a small k value, that is when you could try this and see if it works. Now, the x's that we get rid of are not all the x's, just for practical purposes. If you got rid of all the x's, you have nothing to solve for. But it is really just the x's that you're going to subtract from a number, or even an x that you would have added to a number. So those are the x's that you would get rid of. Any x's kind of by itself are started at 0, you don't get rid of. And the reason for that really is if you started at 0 and you got anything, that is pretty significant, right? Because you had nothing to start with. So even if you got a really small amount of something, it's significant from where you started with. The other ones already had something in terms of pressure in this case. So in this case, we could get rid of the excess there because it's not going to make a big difference in where they end up. But definitely if you started at 0, anything you get is significant. So that's going to take this guy down to 2x squared divided by 0.862 times 0.373. I still need to cube it, equals 4.31 times 10 to the minus 4. Now that looks a lot more manageable, I would think. I'm going to take care of the bottom there and also the top, I guess. So 4x squared divided by basically 0.373 that's cubed, not squared. Hit the right button there, might help. Cubed. Hit the right button correctly. Try it for the 4th time here. There we go. And we're going to times it by 0.862. So that's going to give us 0.04473 is equal to 4.31 times 10 to the minus 4. We're going to multiply that now to the other side. We'll take that 4.31 to the minus 4. Going to get us 4x squared is equal to 0.00001928. We're going to divide by 4, and then I'm going to square root right after it. Yeah, so I'm going to divide by 4 and then square root it. So divide by 4, do a little square root action. Gonna get us an x value here of 0.00220. First off, any questions on that? Now, we made this assumption because our k value is small. How do we know that we could actually do it and it's okay? So whenever you make an assumption like this, you do need to check it to make sure that it is okay. And the normal sort of rule that most people follow and will follow in here is what is sometimes referred to as the 5% rule. And the 5% rule is a way that you could check your assumption to make sure that it is okay. And the way that you check your assumption is you take the X value you just got. So in this case, we had 0.00220. And you divide it by what you were going to subtract it from. So for example, the first guy there, 0.862, you times it by 100%. So this was really the initial concentration, but is also really the number you're going to subtract it from. So you're basically taking 0.00220 divided by 0.862, times it by 100, gonna get you 0.255%. That is less than 5%, which means the check is good and you could use that X value. You could actually do it for both of them. So you could have done it from this guy as well. And for example, since it was 3x, you could have took 3 times 0.00220 and divided it by 0.323, I think. And times it by 100. So even if you did the 3 times 0.00220 and divided by 0.323 times it by 100, you're at 2.0%, also good. In my experience, if you check one is good, you probably don't need to check them all. You'd probably be good by just at least checking one of them. It should be okay. So since we did our check here and it's 5% or less, the check is good and our assumption is good. Now, clearly, if the checking here is over 5% or 5% or more, you then need to go back and solve it some other way. And probably that would be like a quadratic way is probably what you'd have to go back and do that. So now that we have our X value, we could pop that in there. So our pressure of N2 would be 0.862 minus 0.00220. And that's going to get us 0.862 minus 0.00220. It's 0.8, I'll call it 60 atmospheres. Remember, these are pressures, so we'll go atmospheres there. Pressure of H2 is 0.373 minus 3 times our X, 0.00220. So 0.373 minus 3 times 0.00220, gonna get us 0.366 atmospheres. And lastly, our NH3 there. And you can probably see it over there, I think. Pressure of our NH3 is going to be 2 times 0.00220 and 2 times 0.00220, 0.00440 atmospheres in this particular case. And that would give us now our partial pressures of everybody there. And like normal, you should be able to put that back into your equilibrium expression, and you really should get kind of the same value that we started with there. And again, with rounding, it might be a little bit off, obviously, but it should be in the same ballpark. Any questions on the assumption here? So this is 3 different ways that we talked about solving these problems. You could do, obviously, the quadratic. You could do a perfect square if you come across that right. You could do an assumption. There is a 4th way that sometimes books and people will solve these problems. That is known as successive approximation, and we're not going to do that in this class because if you're crappy on it, it'll be a long day for you. But you may see it in a book or a solutions manual. Sometimes they will do it like successive approximation. What successive approximation is essentially kind of what we just did, but you know, for example, that this X value needs to be smaller than that number. So you pick a number and put it in there, and then you solve for the top X, and whatever number you get, if it matches the number you put in there, then that's the correct number. If not, the new number you got, you put back in, and you keep putting a number in and getting a number So the one you put in and the one you get out are the same number, and could be a very long day if you do it a lot of situations. So we will not do it that way, but sometimes books and stuff will solve these problems that way. Question I have though is why did we not do the assumption on the previous three examples? Yes. That's correct. So the K values that we did in the previous three examples, including the one that we did yesterday, the K value was 7, and then the other two were 54.3. Those are large values of K, which means when you reach equilibrium, you should mainly have products, which means the change part is fairly significant for everybody, and you cannot do the assumption on those. So you can only try the assumption if your K value is less than 1, basically. And you should always check it. It will not always work. Yeah. Did you have a question? Yeah. I recommend that if you have trouble with losing zeros along the way, I would probably turn your numbers into scientific notation so you hopefully don't lose them. It would be a good idea. Yeah. Other questions? Other than that, you got to be really, really careful. Yeah. And like the one we did previously where you're kind of working out that quadratic and you're maybe moving some things around and recopying, that's very common when people kind of recopy it, they kind of lose them.